We are going to continue our study of circles by looking at lesson 4, which deals with inscribed angles. We know from previous discussions that the vertex of a central angle is the center of the circle. In this case, it would be point P. I am now going to introduce to you the idea of an inscribed angle. And an inscribed angle has the vertex not at the center, but just somewhere on the circle itself. And it's going to be intercepting an arc as well. So angle ACB is called the inscribed angle, and that inscribed angle is intercepting arc AB. There are going to be two theorems that deal with inscribed angle. The first one is called the inscribed angle theorem. So let's assume that we have the same circle that we saw before, and we have the same inscribed angle C as depicted in front of you. If angle ACB is going to be an inscribed angle, then the measure of angle ACB can be calculated by taking the measure of the inscribed arc and dividing it by 2 or multiplying it by 1/2. And we can actually show the proof of this in a very simple algebraic way. The first thing that we want to do is to draw a radius QB, which is going to be this segment here. And when we draw this segment, we form two things. First, we are going to make a triangle QCB, and we also end up making a central angle AQB. Because the segment that we drew, QB, is a radius, and QC is also a radius, those two segments are congruent to each other, meaning that triangle QCB is an isosceles triangle, and the angles across the congruent sides are going to be congruent. So angle QBC is going to be congruent to angle QCB. If I add those two angles, I'm going to get the exterior angle, which I'm going to be using the letter X for the exterior angle. Because I know that QBC is the same thing as QCB, I can just add QBC plus QBC, or 2 times the measure of angle QCB, equals X. If I divide both sides by 2, I get that the measure of angle QCB is 1/2 times X. Now, X is the measure of the central angle AQB. And the measure of a central angle has to be the same as the measure of its corresponding arc. So the measure of angle ACB is going to equal 1/2 the measure of arc AB. In English, we can say that the measure of an inscribed angle, angle ACB in this case, is half the measure of the intercepted arc, arc AB. And now we're going to look at some examples which show some of the consequences of the inscribed angle theorem. So in the first example, if the measure of arc DG is 45.6, I want to know what is the measure of angle E and what is the measure of angle F. Applying the interior angle theorem, the measure of angle E is going to equal 1/2 the measure of arc DG. DG is going to be 45.6, so 45.6 times 1/2, or 45.6 divided by 2. The measure of angle E is going to be 22.8. Same idea to find the measure of angle F. That's going to be 1/2 the measure of the arc DG. DG is 45.6. 45.6 divided by 2, 22.8. Now, we're given that the arc RT is a semicircle. What is the measure of angle RST? Remember, the semicircle is 180 degrees. Measure of angle S has to equal 1/2 the measure of arc RT. That's the inscribed angle theorem. Measure of arc T is 180. 180 divided by 2 is 90. So the measure of angle S is 90 degrees. And then the last example that I want to look at let's say that we have a quadrilateral inscribed in a circle. So we have a four-sided figure inside of a circle. We're told that the measure of the arc ABC is 184, and the measure of arc BCD is 242. What are the measures of the angles of the quadrilateral ABCD? In other words, I want to know what are all of the four angle measurements: angle measurement A, angle measurement B, C, and D. Measure of angle A is going to be 1/2 the measure of the arc BCD. We're told that the arc BCD measures 242, so just plugging in 242 divided by 2, measure of angle A is 121. Measure of angle D, same. 1/2 times the measure of arc ABC. Arc ABC is 184. 184 divided by 2 is 92. So the measure of angle D is 92 degrees. To find the measure of arc B, that's going to be 1/2 the measure of arc ADC. Now, the measure of arc ADC is going to be 360 minus 84. So if we're looking at the circle, ADC would be this arc. And because I know from finding, or from the problem actually, that ABC, which is this arc over here, is 184, I can just take 360 minus 184 and get the orange arc, which is going to be 88 when you divide it by 2. So the measure of angle B is 88 degrees. And then now that I have 3 angles in a quadrilateral, and I know that if I add up all the angles in a quadrilateral, they have to add up to 360 degrees. 360 minus 121 minus 88 minus 92 give me the last measure of the angle, 59 degrees. So the consequences of the inscribed angle theorem are as follows. If 2 inscribed angles intercept the same arc, those 2 inscribed angles are going to be the same measure. What we saw from the second example was that if an angle inscribes a semicircle, then the angle of the inscribed angle is going to be 90 degrees. And the last consequence is, if you noticed from example 3, angles that are across from each other, such as angle R and angle T, those angles are going to be supplementary to each other. Just like angle U and angle S are also going to be supplementary to each other. So if you didn't notice that the first time we looked at example 3, look at it, add up the angles that are across from each other, and see if in fact they are going to be supplementary, if they are going to add up to 180 degrees. And the second theorem of this chapter has to do with what happens if you make an angle using a segment, such as AE, and a tangent line. So how can we calculate the angle between those two things? Well, it turns out that that angle is going to be 1/2 the measure of the intersected arc. So the measure of angle AED is going to be 1/2 the measure of arc ABE. So it's very similar to the inscribed angle theorem. And with that, we finish the lesson.